let's talk Taylor polynomials. And a Taylor polynomial is a way to take a non-polynomial function like e to the x or sine x, or you can use it for natural logs, and it's a way to rewrite those functions as polynomials in a way that can approximate that function's behavior. And that may make some more sense as we get into this. And then sometimes when you generate your Taylor polynomial or your Taylor series, you can actually look for patterns so that they can be written in sigma notation. And we will look at how that works as well. First, there's some formulas to go with this. And if you're given any function, a Taylor polynomial with whatever desired degree you want, you can make it a quadratic, you can estimate it with a parabola, you can estimate polynomials if you want to go all the way up to like the 12th degree. You can make a 12th degree Taylor polynomial for any function. And it's found by using this formula, which kind of looks scary. So it's you're going to have some center. So we'll say find the Taylor polynomial centered at, say, x equals 1. And that would be c. So you find f of 1, and then f prime of 1 over 1 factorial times x minus 1 to the first power, if that's your c. And then you can go on with the second derivative. And you can use the third derivative, and the fourth derivative, and the fifth derivative. And the more derivatives you use in generating your Taylor polynomial, the more accurately that polynomial will resemble your original function. And we have actually been doing Taylor polynomials all year. I just haven't told you this. If you look at just those terms right there, if I block out everything after the first derivative, what you're actually looking at here is a tangent line. So every time we have done a tangent line in calculus, we have actually been doing a first degree Taylor polynomial, and that tangent line can approximate function values, and that's what we did with linear approximation with tangent lines. And what Taylor polynomials do is it goes beyond just using the slope of the curve for approximations, and you can actually pull in the second derivative of the curve, which then starts to factor in the concavity. And then if you want to pull in the third derivative, you're looking at what's called the jerk, an extra little whip that makes the function, the Taylor polynomial, resemble the function. And so I'm going to try to illustrate that or show you an illustration of how that works by looking at the function sine x, which is obviously the red graph. And what we're looking at right now with the blue line is the line tangent to sine x at x equals 0. That is also known as the first degree Taylor polynomial approximation. And you can see that if I stay pretty close to that point of tangency, this line is fairly close to the graph of sine x. However, if I get further away, this line gets further and further away from the actual function, and that tangent line becomes a bad choice if I want to approximate, say, a sine of 2. I can look over here and I can see that at 2, my sine graph is pretty far away from the tangent line. But what if we could increase the accuracy of this approximation by bringing in more derivatives? And if I bring in more derivatives, I just had somebody knock on my door and I lost my train of thought. So I think what I was talking about here is if I add more derivatives and look at more characteristics of sine x when getting this approximation function, you can see that it starts to hug the graph a little bit further. So let's step this up. And if I go to the next derivative with sine, it actually skips the x squared, and sine only shows the odd exponent. So right now I'm looking at a degree of 1, that's x to the first. And with my next iteration of Taylor's polynomial, we get a cubic function. And you can see if I use a cubic approximation, all of a sudden we are hugging my sine graph a little bit further. And that's only going to a third degree. If I step that up to a fifth degree approximation, here's the fifth degree, and you'll see that it allows for more curvature in the approximation function. And that Taylor polynomial now, if I'm looking here at x equals 2, now we're really close. And if I keep going, if I keep adding derivatives and keep allowing this Taylor polynomial to whip itself around the sine graph, you can see that with enough derivatives, you can see that my Taylor polynomial is very, very good at approximating the graph of sine x. So that's kind of what Taylor polynomials do. And here is, let's leave that. Here is the formula that we'll use, and c is going to be some point that will be given to you in the Taylor approximation. So let's look at how this would work, and I want to start by finding the third degree Taylor polynomial for the function y equals ln x centered at x equals 1. And to do that, we will use this formula right here. I need the nth derivative at 1 in this case over n factorial times x minus 1 to the n. So I'm going to replace these c's with a 1. And to do that, if I need the third degree, I'm going to have to go to the third derivative so that I have an x minus 1 to the third power. And so what I'll do is I'll create a little table here. And assuming you are sufficiently good at derivatives, I went ahead and I found all of the necessary derivatives. So the 0th derivative is just your function. Then I have the first, second, and third derivatives of ln x. And then for this formula, I need the nth derivative at 1 divided by n factorial. And that's what I have in this column. So ln of 1 is 0. 1 over 1 is 1. Negative 1 over 1 squared is negative 1. And then I'm also dividing by n factorial. And I went ahead and cleaned those up. It didn't take a whole lot of effort there, but it's 0, 1, negative 1 half, and 1/3. And for this problem, my Taylor polynomial approximation for natural log x, and I'll say natural log x is approximately, and it would be my function at 0, so that'll be 0 is my first term, plus 1, that was where I got when n equals 1, times x minus 1 to the first, plus my next coefficient was negative 1/2, so I'll make that minus 1/2 times x minus 1 squared. And then when n was 3, my third derivative at 1 divided by 3 factorial ended up being 1/3 times x minus 1 cubed. And that is the third degree Taylor polynomial approximation for the natural log of x. And it is an approximation. And as long as you stay relatively close to that center, you get really good approximations with Taylor polynomials. So that is a third degree Taylor polynomial for ln x centered at x equals 1. Now let's look at some other types of Taylor polynomials, and one of those is actually the other one that we're going to look at in BC is a Maclaurin polynomial. So Maclaurin is a mathematician. He did a lot of work with Taylor polynomials that were centered at 0, and so they named those polynomials after Mr. Maclaurin. So a Maclaurin polynomial is nothing more than a Taylor polynomial with a center of 0, which makes them very easy to work with. And a Taylor or a Maclaurin series, notice I'm changing from the word polynomial to series, those are polynomials that do follow a very distinct pattern and can end up being written in sigma notation like this. Some polynomials, while you can expand them, the pattern is a little bit more difficult to follow, and you may not be able to easily find a pattern to write it as a series, but that's what a series would be. And you'll notice it's the same formula. It's the nth derivative at c over n factorial times x minus c to the n, and we'll just put that inside a sigma, inside the series notation for a Taylor or a Maclaurin series, depending on what the value of c is. Okay, so let's look at two more examples with Taylor series, and both of these will be Maclaurin series. The first one says Taylor series centered at 0, which means it is a Maclaurin series as well. And I want to find the general series for e to the x. Notice I didn't specify a certain degree polynomial. I didn't say go to the third degree or the fourth degree. I want you to do enough of this series so that you can identify some type of a pattern and write the series for e to the x in sigma notation. So, same thing with the table. I'm going to assume you're pretty good at derivatives, especially for e to the x, and your derivatives all the way down. I went to the fifth derivative because I wanted to go far enough that I could possibly see a pattern when I started to look at my nth derivative at 0 over n factorial. And when I'm looking for a pattern, I a lot of times will not simplify it completely. I would almost rather see it in terms of factorial. So I left it as 2 factorial, 3 factorial, 4 factorial. I'm not going to clean that up any. And so I know the formula for a Maclaurin series or a Taylor series is this, and because this is Maclaurin, we can replace these c's with a 0, and that is what I'm going to be looking for. I'm going to try to find the pattern here, and so it's going to start with n equaling 0 would be 1 plus, and then when n equals 1, it will be 1 over 1 factorial times x to the 0 of 1 to the first power, because I am doing x minus 0. My next term is 1 over 2 factorial times x to the second power. Then my next term, my coefficient is 1 over 3 factorial times x minus 0 to the third power plus, and my next one is 1 over 4 factorial, and I'm not even going to bother writing the fifth degree term because this is a series that has a fairly easy to recognize pattern, and I notice that I am always doing x to the n power over n factorial. And if you look at each of these terms, n equals 0, n equals 1, n equals 2. This is a pretty nice clean pattern. And that is your series for e to the x. So it turns out that e to the x is equal to the series of x to the n over n factorial as n goes from 0 to infinity. And that is one of 3 series I strongly recommend you memorize. The other 2 are sine x and cosine x. Some teachers like to add a couple more to the mix, but those to me are the 3 biggies: e to the x, sine x, and cosine x. And there is e to the x. In AP Calculus, you're expected to have that memorized, so you don't have to generate that. You don't have to prove how you know that this is the series for e to the x. It is an expected series for you to just have memorized. So write that down, study it, and memorize it. There's your Taylor series for e to the x. Let's move on, and I believe this is, yes, this is the last one I want to look at, and I want to look at the Maclaurin series. So again, we're centered at x equals 0. So make a note of that. So Maclaurin series centered. How did I spell centered there? Centered. I did it again. There's an E in there. At x equals 0. And we're looking at the series sine x. And so my Maclaurin series, if we're centered at x equals 0, then that can be written, n goes from 0 to infinity, the nth derivative at 0 over n factorial times x minus 0 to the nth power. So that's what I'm hoping to be able to identify a pattern and write it like that. And I've gone ahead and I've cranked out my first 5 derivatives of sine x. A little bit more difficult than e to the x, but it is cyclical. So we have those first 5 derivatives. And then I need to evaluate those derivatives at 0 and divide them by n factorial so that I can have this coefficient of x to the n. And if you look at those, when I start plugging in, you'll notice that for this series, for sine x, and I mentioned this earlier, it does skip the even power terms. And so you're always going to have an odd power polynomial approximation. And if you look back at that animation I showed earlier, you'll notice that those polynomials always had opposites in behavior, odd power polynomials, or odd degree polynomials, and all of my evens are gone. So that term is 0, 0, 0. And I'm noticing now if I look at my polynomial, I can expand it and it will be written as 1 divided by 1. Actually, I'm going to write 1 over 1 factorial. 1 over 1 factorial times x to the first minus 1 over 3 factorial times x to the third plus 1 over 5 factorial times x to the fifth. And I see my pattern. I'm going up by odd powers, and it's 1 over something factorial times x to that same power by the odds. So that's, the next one's going to be minus 1 over 7 factorial, x to the 7th, plus so on and so forth. And so I'm looking at this, trying to unpack it, and I realize that in my table over here, my x to the first power corresponded with n equals 1, x to the third power corresponded to n equals 3. However, when I'm trying to come up with a formula, I'm going to just reset this at 0. This will be when n is equal to 1. This will be when n is equal to 2. This one's going to be when n is equal to 3. And I'm going to write my series and my sigma notation based on these n values, not the ones that I used in the table to get those first several terms. And the pattern that I'm seeing here is the series does alternate, so I will need a negative 1 to the n power, and then it's x, and I'm going up by odds. And if I want a formula that goes from 1 to 3 to 5 to 7, we're increasing by 2 each time. And so that's going to be 2n plus 1 is going to work. So if I plug in 0 for n, 2 times 0 plus 1 is 1. If I plug in 1, 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5. So that's working out. The denominator is 2n plus 1 factorial. And then I'm going to make sure that I'm starting with the right sign term. I need to start with a positive term. So I'm going to test this really quickly. If I plug in 0 for n, that does turn this into a positive 1. That does start me with a positive first term. And this is your series for sine x. Right there. That is another one you need to memorize. And I'll write down the series for cosine x in just a minute. But there's your series for sine x. But we're not done yet because this question asks us not just to find the series, but to find the radius and interval of convergence for this series. So let's look at that. So for radius and interval of convergence, if it's a geometric series, my 2n plus 1 didn't copy over. If it's a geometric series, then you can just look at the ratio. However, this is not geometric, so we do have to go on with the full ratio test. So let's set up the ratio test and start canceling and see what we end up with the ratio test. And I can assume, hopefully, that you know how to set up your ratio test. And so I went ahead and set this up while the video was paused. And 2 times n plus 1 plus 1, when I plug in n plus 1 for n here, you can see that is 2n plus 3. So we have our ratio test set up, and now we need to start seeing what can be divided out. I have an error right here. Oh, no, I don't. Never mind. I'm looking at the wrong thing. Never mind. Everything's good. Looking at my x's, I have 2 more x's on top than I have on bottom. I have 2n plus 3 on top, 2n plus 1 on bottom. So these will divide out all but 2 of these. So I'm going to try to be very careful on keeping the x squared. Negative 1 to the n, I have 1 more negative 1 on top. So this is going to cancel all but the negative 1 here. 2n plus 1 factorial, 2n plus 3 factorial. This term is 2 more than that one. So when I cancel the factorials, I'll be left with a 2n plus 3 and a 2n plus 2 down here. So this is going to cancel all of that and leave those 2 terms. And then the absolute values will get rid of that negative 1. So now I'm down to the limit as n goes to infinity. In the numerator, I have just an x squared. In the denominator, I have the 2n plus 3 and the 2n plus 2. And as n goes to infinity, my bottom degree is 2. I have an n squared down here. There are no n's on top. And so this limit will equal 0. And for the ratio test, you need your limit to be less than 1. And I believe 0 is indeed less than 1, regardless of what I plug in for x. So that means that my radius of convergence is infinite. We go on forever. And the interval of convergence is negative infinity to infinity, meaning that you can use your Maclaurin series for sine x for all values of x. Doesn't matter how far away you want to get from that center, you can actually use the Maclaurin series for sine x on everything. And that is also true for e to the x, and that is also true for sine x, or cosine x. All of the series for those 3, you have an infinite radius of convergence. So I guess I can say the radius of convergence is infinity as well. So there's a fairly lengthy, I try to keep my videos closer to 15 minutes, but here we are pushing 18 now. So there is Taylor and Maclaurin series. And just for the record, I'm going to throw down cosine x right here. So hang on, I'm actually just going to copy and paste it so you can read it more easily. There we go. So there's cosine x. Now let's go ahead and grab sine x and e to the x as well. So those are the big 3 for me. Some teachers like you to memorize 1 over 1 minus x. Some teachers like to memorize the natural log of 1 minus x. There are some others that you may see memorized formulas for out there on the internet. But in my opinion, these are the big 3. So know these, and then we will use these in class.